And so next speaker is Per Greenfield. Perry Greenfield is a senior scientist and has worked with STScI in Baltimore since 1985. And he's going to talk about the Advanced Scientific Data Format, ASDF, and why you should use it.
All right, thank you. As mentioned, I'm at the Space Telescope Science Institute. My goal in this is to basically give you the highlights of what this data format can do, and the background to it, and why you might find it interesting. The time I have is not nearly enough to cover all the details, so I can only hit some of the highlights of this. So what drove us to do this? Basically, in doing the HST pipelines, we ran into a lot of frustrations. And the biggest one probably was in dealing with WCSs for unresampled data. We tried very hard to work within the system, and it just caused us a great deal of problems. And we ended up with a solution that really wasn't a standard one anyway. We saw no way forward, and ultimately came to the conclusion that we needed something better. You don't create a new format. You don't take that lightly. And I think a lot of people think you'd have to be crazy to try to do something like that. And I guess we're a little crazy. Somebody, I think in the end, somebody's got to do it. And at least that's our view. And so let me talk about what we were seeking in a new format. One of the things that we found annoying is not being able to represent hierarchies and groupings in a simple way, and not relying on conventions to indicate, this belongs with that and all that. A lot of those things should be basically implicit in the data structure that you're working for. On the other hand, we still need, it still has to be useful for binary data, and that's an important detail. It's also important that it leverage a lot of existing tools. We don't want to reinvent the universe here. Extensibility was very important, not just in a standard, but if people had local needs that they needed to adapt to. I'll talk a little bit more about this later. It had to be easy to adapt to those. Important to us was also being able to validate that files are correct. And so that was yet another aspect. And of course, I mentioned before, being able to deal with complex WCS models was perhaps the biggest driver. And we would, and like FITS, we would like this to be an archival format as also. The solution we chose, excuse me, was to base it on YAML. We chose YAML over JSON, mainly because it's more readable, more concise. They have a close relationship to each other, and particularly because the YAML has support for a couple features that JSON doesn't have it intrinsically. The YAML in these files holds all the basically the metadata and the structural relationships of all the binary data as well. So I'll show you a very simple example. Of an ASDF file. It starts out with some header information about versions and things like this. And the real content starts down where I'm showing the cursor. And you can see, it's a pretty understandable arrangement of information. You have keys and values. You can also, so the thing I want to highlight here is, for example, here's under powers, there's something called squares. And this item here is a YAML tag. And a YAML tag is used to indicate that what follows is to be interpreted in a special way. This is essentially typing information. And in this case, it's saying what follows describes an array. And the information for, in this particular case, is a binary array. So the actual data is found in a binary block. And so this tells you which block, what kind of data is in the array. It's in 64, what the, the dimensions of the array are and all that. Here's another array. And the difference in this case is, it's exactly the same type, but the data are inline. So this transparently represents both inline arrays, so that can be completely text, or it can be a large, very large binary array appended to the YAML. And the reason we wanted to support this is lots of people like to start out, for example, with tables that they want as completely text, but maybe they reach a point where it makes more sense to make it binary. ASDF would let you very easily convert from one to the other without changing the software interface to access that data. But anyway, this gives you a flavor of what the format looks like, at least in the header. So the highlight, I'm not going to read through all these in detail. I've highlighted particular things here that might be irrelevant importance. Obviously, one of the things is you're not restricted to the fits keyword size names or even values. I mean, values can be complex structures, as you saw for arrays. And the tag feature allows the software to, when it opens a file, to turn those particular substructures into objects in the language. So in Python, for example, those arrays are turned into NumPy arrays. In a different language, they could be turned into whatever the normal representation for arrays is in that language. And so we consider this a very powerful feature. The other aspect of it is that it also, this is a part of the extensibility I'll talk about a little bit later. It supports schemas. It's layered on JSON schema. And so you can validate the files if you have a very specific requirement for them. It allows for extremely flexible WCS models and models in general. It's extensible. You can publish basically, in a tag gives information about where the schema information for that tag is, and also, which also can be used to determine what software you need to interpret that. If you don't happen to have that software, it just reads it as sort of normal YAML. So it won't prevent you from reading the file. It's a generic format, and it really isn't limited to just astronomy. So we would like to see it used in a wider context. Right now, it's used for JWST. It's going to be used with the Roman Space Telescope as a native format in the pipeline. It can also be run as a native format in the JWST pipeline as well. Also being used by DKIST, Gemini Dragons. LSST is using it for the WCS interchange format. We've had some users outside of astronomy already.
33 minutes now.
Okay. We're working on a version 2.0 standard that incorporates certain things, the lessons learned from this. Right now, I mean, the idea is that this is language independent. Currently, though, we only support it in Python. We would like to develop a C++ version of it. We've improved the API in the library. We've added a lot of things to make it easier for users to interactively look for data, information in the YAML. We've made the standard, moved it to a neutral site, and oops. So a few more things to talk about. We would like to, one of the things that YAML doesn't really handle well are comments. And so we would like to be able to extract comments from the schema. So if people want more information on what a metadata means or what a data item represents, that it'll easily be able to extract that from the schema. We'd like to support chunking in BLASK in the next year. It's necessary for the Roman telescope. We also plan to put IDL support in, be able to display ASDF and DS9. The last item I'm going to say is something that I have a sort of desire for. I don't know how easy or whether it would happen. You know, what we've seen in FITS is that there are lots of variants, particularly in spectral data, lots of variants of the same kind of data, but everybody has to interpret the files in different ways. If we can help develop a sort of standard approach, data models in a sense, that grow organically through these analysis routines, then we can sort of unify all these variants into one kind of data file that a lot of analysis and other kinds of programs can interpret. So that's basically where we're headed with this. I hope you find that there's a lot of useful things in this. I see that it's both very general, but also fairly easily understood. I mean, one of the things about this is that I think if somebody came along, if you avoided using exotic binary representations, stored images simply, tables simply, that somebody coming across these files would be able to fairly easily interpret them without any documentation whatsoever. And at that point, I'll just show a slide on where there's more information. Presumably we'll put these slides up someplace so that you can access this. And at this point, I'll stop here and take any questions if there are any questions.
Thank you, Perry, for fitting perfectly your time slot. If there are any questions, please put them on the question and answer box for the time. Perfect. Francois Bonarelli is asking, how does WCS look like in ASDF?
That's normally, I would, while this format allows nesting of things, you don't want to over nest things. But one area where nesting is a natural thing is we allow expressions in the WCS transforms. So you can combine things into complex expressions. So they're basically shown as expression trees in the YAML. So, you have essentially a series of binary operations that combine, one model with another, or pipeline one model into another, combine dimensions into things. So that's a fair, if you were to actually look at the YAML of that, you might see a moderately complex structure. That's not something we expect people to have to look at. That's one of the things that I think is meant to be more opaque to people. But, if you read it, you would understand exactly what was going on if you, broke it down.
Reinhardt is asking, where are the binary blobs referred to in the YAML file actually stored and found?
They're at the end of the file. They start after the YAML. There's actually a little index of where the blocks are and what their offsets are that are used to, access individual blocks. But you don't have to have any blocks. But if you do, you can have any number of blocks that are appended to the file. Those blocks can be compressed. There are a lot, we expect to support lots of options, but you can store them as simple arrays and things like that. But basically, every array goes into its own block. We do allow, and one of the things that ASDF allows is views into blocks. And so the other feature of YAML I didn't refer to is are references in the sense that multiple things, attributes can actually point to the same thing. So you can avoid copying identical information over and over again. And it's also with arrays. You can, in another item, you could show an array, let's say a cutout, and use the same exact array that has a full image without actually copying the data. So they would both refer to the same block, just in a different way.
And a very final yes or no type question by Alexander. Are there plans to include it in the AstroPy environment?
We already have routines to access it through AstroPy. While we're developing, this is a standard issue, if it's included in AstroPi, you're locked to the AstroPi release cycle. I think it's early enough that we don't want that locking to happen. But at some point, it may make sense to be part of AstroPi. It's intended to be entirely compatible with AstroPi. And, if you look in AstroPi, there are certain things in AstroPi that are rendered, like modeling models are rendered into ASDF, as are coordinates and a few other things in AstroPi. So but right now it's on a different release cycle, and that makes it a little more flexible for us to make changes.
All right, thank you again, Perry.